In this video I'm going to calculate a transmission function for a set of survey spectra measured at different path energies. This is the same type of data set that I used previously to calculate a transmission function that was based on regions. In this instance I'm going to make use of regions, but the region's function is slightly different. Instead of calculating for each region an area and a kinetic energy, I'm going to use the intensity of each data bin within a region and the kinetic energy for the data bin in each region. So what I'm doing is increasing the number of data points within the set of data that I'm going to use to obtain the transmission function by fitting a cubic polynomial. To create the transmission function, I'm going to have to manipulate these data to put them in the right form for the intensity calibration option that I'm about to use. The first thing I need to do is extract the background signal only, and I can do that by overlaying in the active tile all these spectra that have identical regions and then using the button that says spectra from regions. A new file will be created and each one of these regions is now in a row for each path energy. So when I overlay by row, I can see all these different sets of data that can be used to calculate the transmission function, but they're still not in a form that is suitable for this calculation. They all must have the same number of data bins. As it happens, the way these data were acquired, the number of data bins changed as a function of the path energy. There were more data bins in the lower path energies, so you see the energy resolution of peaks. Now in this instance that's not what we need. We need them all, the intensity must be at the same energy, and therefore I'm going to rebin the data based on the selection you see in the right hand side, and what this will do, adjust all the intensities so they all now have the same number of data bins and the intensity has been calculated appropriately for these data bins from the data in the previous file. So now I can construct VAMAS blocks for each row by displaying the rows in the scroll list. Each row receives a separate tile, and that's exactly the format that I need to create a new VAMAS file containing one VAMAS block per row. So these all will correspond to the different path energies, and now I have the data. It's in a form that I can use for the intensity calibration option, and that involves the intensity calibration property page on the spectrum processing dialog window. This button will calculate from regions the transmission function. However, the second button will look at the data in the selected VAMAS blocks. So I have selected VAMAS blocks and I press the button, and the result is a new VAMAS file in which a transmission function has been calculated. And there we have the shape of the transmission function, and the values for the coefficients have been entered into the intensity calibration property page under the VG transmission coefficients. So we can apply this transmission function to the original data. So let's go back to the original data, and I'm going to copy that to a new file. I'll take the process data only, so I leave all the regions behind. Then if I overlay these data to see how, as a function of the path energy, the intensity changes within these spectra. So they're not at all equivalent right now, but once we apply the transmission function and then apply the transmission function to the data, so we have intensity. In terms of intensity they are still different, but in terms of counts per second they are the same. And this is how we do quantification. What we need is the same area of a peak in counts per second EV. I'll now demonstrate how the transmission function is used to calculate areas of the photo emission peaks. So let's go back to the original data, and what we'll do is we will copy these data to a new file. I'll use process data only because that way I lose the regions that were defined. And what I would like to do is update the VAMAS blocks with two regions, and these regions are going to be for the zinc 2p 3 halves. Let me identify that as here, and then using the element library, zoom and create when selected. So we have a region that can be defined on the zinc 2p 3 halves, and I want to do the same thing for the zinc 3p. Now the idea of identifying signal from the same element using different photo emission lines is it really demonstrates how quantification works. Both peaks ought to give the same answer. So when we compare the area of the 3p and the 2p, we ought to get a one-to-one relationship. So we've got now the necessary regions with the relative sensitivity factors that have been adjusted for the angular distribution for this instrument, and I need to propagate those. But before I propagate, what I want to do is make sure that, since I'm using Schofield cross sections, I also want to have the escape depth correction active. The Schofield cross sections assumes that you do not have a bulk material but a thin film, so when we have a thick sample such as this zinc foil, then we ought to correct for the escape depth. So having selected these, I can adjust to one of these options for the escape depth. So now I can see that I have the transmission function active, and I have the escape depth is now active. So what I need to do now is propagate the regions. If I overlay these, we can see that they are all set up. Let's just check that the regions look reasonable, and they do. Okay, so that will be a reasonable measure of the amount of zinc from either one of these photo emission peaks. I'm going to have to bring up the intensity calibration property page and apply the transmission function. Let's have a look at that. Have I got these selected? I do. I need to press the button that says change VG transmission function. This will update the transmission function in these with the new coefficients, and as a result I can perform quantification based on these two regions. I should get 50-50 for the quantification, but more importantly I should get the same area calculated for all of these. Even though you can see the intensity itself is wildly different in terms of counts per second, the transmission function is going to make the necessary correction to allow the same area to be calculated from each one of these spectra if it works. So let's apply, and we do get very much a consistent answer from these two zinc peaks. Okay, the pass energy 26 is not perfect, but if we look at the area, this is more important. This area needs to be the same, and that is reasonably true for the pass energies that we would probably use for quantification and working with. So we're quite happy now that they are reasonably consistent in terms of area and results.